Thank you so much for joining this lesson. We're going to discuss the color pre-trial examination 2025, a very serious exam, and I hope you guys are going to benefit from this. Color is for the Kenya High, Alliance High, Lenana High, and Alliance Girls. So that's a joint exam for the 4 schools. Cooperate through this session until the end. Look at number 1. A lady standing in front of a mirror sees an upright image. That is one characteristic. That is of the same size as herself. The second characteristic. State the type of the mirror she was using. So according to these properties or the characteristics of the image she's able to see, we can confidently conclude that she is in front of a plain mirror. This is a plain mirror. So there are other common characteristics of images formed in a plane mirror, like a lateral inversion. When you say the image was laterally inverted, means if you're in front of the mirror and you raise up your right hand, the image you are seeing raises up its left hand. Like you are laterally inverted. Your left is to the right, according to the image. So that is what we call lateral inversion. Same size, it is also supposed to be same distance behind the mirror as you are in front of the mirror. So those are some of the properties of images formed when an object is in front of a plane mirror. Number 2, the figure below shows a ferromagnetic material with ends PQ being magnetized using a magnet whose polarity is indicated in the diagram. So we can see the permanent magnet, the magnetic material with ends P and Q, then the path being used. And number 1, we are told to state the method of magnetization being used. This is called single stroke method. Single stroke method. It's good for you to know that when 2 magnets are used in this manner, we call it, if we had another magnet here, for example, now being moved to the opposite direction, as this one goes to the right, we have another one flowing to the left. That one would have been double stroke. Therefore, if you say that this method is stroking method, then you lose the mark because it is specifically single stroke method, not just stroking. So it's good for you to know that you have to be specific when called to be specific. Like in our case here, it's also good to know that when we say a ferromagnetic material, this is a magnetic material with a very strong attraction to the magnet. Magnetic materials are all attracted to magnets, or magnets attract magnetic materials, but there are those materials with a stronger attraction than others. We call them ferromagnetic. All right. State the polarity acquired at P. State the polarity acquired at P. So at P, there will be some polarity, but let's focus at Q first. At Q, this is where the stroking is ending. And we usually say, where the stroking ends, that particular end of the material being magnetized by stroking method acquires a polarity opposite to the end of the magnet. So the end of the magnet that will sweep at this end shall be a north. That means the end here will be acquired as a south. And now that a south has been acquired at Q, automatically at P, we shall get a north. At P, we shall get a north pole. At P, we expect a north pole. Now at number 3, ladies and gentlemen, remember to subscribe to the platform. Remember to share, invite a friend kindly. Let's know where you're watching us from. Now we are on a light, or rather, we are on geometrical optics. Remember, every topic in physics can be traced into a particular branch of physics, depending on what it is covering. For example, here, we are dealing with the behavior of light, and we know the branch of physics that deals with the behavior of light as it traverses from one media to another is called geometrical optics or geometric optics. So now we are on geometric optics after electricity and magnetism. And even in number one, we were on geometric optics. So depending on the content in a topic, we can trace that topic back to a particular branch of physics. State the nature of the defect. According to the rays, which are parallel here, the rays are from a distant object. Rays from a far object. Rays from a far object. So if these are rays from a far object, and you can see very well that the image is not being focused at the retina, the rays are meeting before the retina. State the nature of the defect. If far objects, the rays cannot be focused at the retina, then this person is short-sighted. So this is short sight. This is short sight. Short-sightedness. Scientifically, we can call it myopia. Scientifically, we call it myopia. Yeah, this is myopia. Myopia. Leave a comment, please, as you continue following. Let's know where you're watching us from. Let's know your school. Let's know your physics teacher. Cheers to your physics teacher, please, as we continue learning. State one possible cause of the defect above. One possible cause of the defect above. What might have led to this? One is a long eyeball, the general diameter of the eye. If it is too long, rays might intersect before they reach at the retina. So we talk about long eyeball as a possible cause. Another cause might be what we call short focal length of the eye lens. Another possible cause is short focal length of the eye lens. Yeah, the eye has a lens which is responsible of refracting light so that the rays might intersect at the retina to form what you're calling the image for the person to observe when the image is interpreted at the brain. But now we are asking ourselves, how is shortness of the focal length of the eye lens affecting the person to make him a short-sighted one? You should know that there is something called the power of a lens. The power of a lens is given by the reciprocal of the focal length of the eye. Therefore, if it is given by the reciprocal of the focal length of the eye, then it means the smaller or the shorter the focal length, the greater the power. So it means this person is having a possibility of having a short focal length that leads to a very high power of the lens. When the lens is powerful, we say that it has a great refractive ability. It refracts light so much. So it's bending the light too much. That way, it might cause the rays of light, because of the much bending, it might lead to the rays intersecting before they reach the retina because of the great refraction caused by the eye lens, which is having a high power due to a short focal length. I hope we are together at that. Yeah, it's my hope that we are together at that. So we would need now to state the property of the lens to state the appropriate lens to correct the defect. And this is going to be what we call a diverging lens. So we would need a diverging lens to correct this. Remember, it's also called the concave lens. It's also good to be very careful. The names of these mirrors, the lenses, sorry, and the mirrors in book 2 physics try to confuse some learners because diverging lens is called concave lens, whereas in reflection at curved surfaces, diverging lens is called convex lens. In form 2, let me make it clear. In form 2, a diverging mirror, a diverging curved mirror is called convex mirror. But a diverging lens is concave lens. Converging lens is called convex, but converging mirror is called concave mirror. So let's master that slight difference. Much invitation to our programs for the August. Please enroll. Remember, our number is attached to the wall here, 0704 15 3366. Please get the best from this particular program. We are organizing the best. Tutors will be the best. And I am sure learners are enrolling actually. Please be part of the great team which is learning this August. All the best as you continue to plan to partner with us in a very great way. My number, as I repeat, it's 0704 15 3366. So that is the number you should inquire about the programs through. I would encourage you to use the WhatsApp kindly so that we may communicate effectively. Look at number 3. An object placed 15 centimeters from a concave mirror forms an upright image which is magnified 2 times. Look at that. Magnified 2 times. Some other language that can be used there. You can be told this particular image is twice the height of the object. That would mean a magnification of 2. Determine the focal length of the mirror. So here we are saying that magnification is 2. And how do we get magnification? Basically, distance of the object, distance of the image out of distance of object. So this 2 is given by the known image distance out of the known object distance. Object distance is where the object is placed in front of the mirror. Therefore, there is a V of 30 centimeters. The image is formed 30 centimeters from the mirror. Now, if that is so, then we would go to what we call the mirror formula. This time around, we are calling it, it's a mirror, not a lens, the mirror formula. So in the mirror formula, we say 1 out of F. F is the focal length, equals to 1 over V plus 1 out of U. And we have all this, so that we say 1 over F is given by 1 over F is given by 1 out of, okay, let's be realistic now. Let's be realistic. An upright image. You know, it means this image, for it to be upright, if you study the properties well in a concave mirror, it means the object is within F. It is between the, what we call the principal focus and the mirror itself. That is why an upright image in a concave mirror is being formed, and this particular image is magnified and on the opposite side, behind the mirror, in other words. So if it's behind the mirror, then it means definitely it's virtual. It is a virtual image. So this one is virtual. And for virtual distances, we give them a negative. So negative 1 over 30. Instead of 30 now, we use a negative. The negative is being introduced due to the negative is being introduced due to the virtual nature, of the image. Then plus 1 over 15. And we're going to get 1 over f is equal to 1 over 30. And therefore, f equals to 30 centimeters. This is a very interesting lesson. Very interesting. We get to number 4, still from to work. The figure below shows two parallel current carrying conductors placed close to each other. Use it to answer the questions that follow. So we can see the two current conductors. You can see them, and current is out of the paper. It's good for you to know that. Current is out of the paper. Into the paper would have been a star into the paper across that way. So when it is a dot, it's outside the paper. Sketch magnetic field patterns around the conductors. So magnetic field patterns, what we will see is that the magnetic field patterns will be interacting in a particular way. They'll be interacting in a particular way. Of course, they first form circular loops. But as they continue approaching one another, we expect them to start interacting. I don't know what is interfering with my screen, but I hope you guys can read something from that end. As they continue getting closer to one another now, they will start interacting. And now the field lines will be emerging from here. Yeah, they start forming complete loops. Now they start forming complete loops. That way. So we will have them now moving in this kind of a direction. This is now the direction that you'll be having that way. So that's how they will move. That is how they are expected to move. Yeah, that's how the field is going to be moving. Then we are also told to sketch magnetic. Okay, we have sketched. Then on the same diagram, we indicate the direction of the force acting on the conductors. The force acting on the conductors, for this one, we'll have a force moving in this direction. And for the other one, a force in the opposite direction. Yeah, a force in the opposite direction. Force will be in the opposite direction. So you see, if, for example, I use the first one here, I would say current is out of the paper. I'm using this one. Current is out of the paper. That is according to the second finger. Then, if current is out of the paper, then I would expect the magnetic field lines to be facing upwards at this point, and definitely the force, according to the left-hand rule, Fleming's left-hand rule, shall be towards the left. That way. So refer to your book too, please. Give a reason why it is necessary to leave the caps of the cells open when charging an accumulator. And this is to ensure that we expel the oxygen gases and also the hydrogen gas produced during charging. So this is to expel the oxygen and hydrogen gases produced during charging. So during the charging process, we have oxygen gas, hydrogen gas being produced. And wait, are you a subscribed member to Shifting Grades? Have you really asked yourself that question? Are you a subscribed member of Shifting Grades? Have you ever invited a friend to Shifting Grades? Are you learning? Are you benefiting from Shifting Grades? Let's know from the comments that you're giving. Let's understand where you're watching us from, and let's know whether you're getting something from our platform. Please remember to tag your place, tag your school. Please recognize your great institution. That is the school that is making you the person you are. That is the school which is converting you from a boy to a man. That is the school which is converting you from a girl to a great lady in the community. So please, let's recognize our schools respectively. Tell us where you're coming from. Thank you so much for your cooperation. I hope you shall be found tomorrow. I hope you shall be found here another time. And all the best, by the way, to the candidates who are pursuing the exams this year. All the best to anyone who is preparing for national examinations, end term exams, whatever exams. We wish you well. Anybody who is seeking knowledge, I know I have even tutors here. I have teachers who are really supporting my program, and I really appreciate that. So thank you so much. You are most invited to our August programs. You are highly invited to our August programs. And I really hope that you guys shall get the best. Please enroll. Please enroll. Just use the number attached 0704153366 and you shall get the best. Number six, ladies and gentlemen, an electric bulb rated 40 watts is operating on 240 volts mains. So this is power, this is voltage. Determine the resistance of its filament. We should know that power, according to heating effect of an electric current, that's Form 3 work. Heating effect of an electric current. Power is usually given by V squared over R. Of course, we have equations that lead to this, and that is, we know that according to the definition of electrical power, it's given by VI. Then again, we know that according to Ohm's law, V equals to IR. And therefore, according to this, then current is given by V out of R. Therefore, we will talk about power now being given by V, and instead of I, talk of V over R. Instead of I now, according to the Ohm's law. So this is where V now becomes squared. Then R is the denominator. And from what we are having, we would say 40 is equal to 240 squared out of a known R. So when we want to get R, we'll be getting 240 squared divided by 40. Then we get 1,440 ohms being resistance. Remember to give the right units and also the right signpost to the units. 140 ohms, since this is resistance, electrical resistance. Yeah, we are still on electricity and magnetism. Number 7 now. The figure below shows part of an electric circuit with 3 resistors. So we are having a resistor of 10, another one of 10, and another one of 18. Determine the effective resistance in the circuit above. So in this particular electrical circuit, we're supposed to determine what we call effective resistance. These ones are only 2. They are only 2 resistors and they are parallel to one another. When resistors are parallel to one another and they are only 2, Then we say this, effective resistance is given by resistor 1 times resistor 2 out of resistor 1 plus resistor 2. When they are only two, this is a special case for parallel resistors. Sorry, I was to confuse them with capacitors. But for parallel resistors, we say that when they are only two, and master that, we are applying this for only two. Effective resistance is given by product 10 times 10 out of sum 10 plus 10. So we are talking of 100 over 20. 100 over 20, and 100 over 20 will give us automatically 5. So we have 5 ohms. So it will now be fair for us to say 10 and 10 in parallel are equivalent to a 5 ohm resistor. So now we are having 5 ohm connected in series with our 18 ohm. So 18 ohm now connects with a 5 ohm that way. And so now we will now say that in series connection, regardless of the number, effective resistance is usually the sum or total resistance equals to 5 plus 18. This shall lead us to 23. That one will lead us to 23. So that is the final answer. About the parallel, let me mention, because I've already emphasized that in series, we just take the addition. Then in parallel, we say that 1 out of the effective resistance is given by 1 over R1 plus 1 over R2 plus we continue adding until we get to the last one, if they are in parallel, because they can be more than 2. So when they are 2, we can still use this general so that people may not confuse. 1 out of resistance total would be equal to 1 over 10 plus 1 over 10. So 1 out of the total resistance equals to, when I take 1 out of 10 and I add 1 over 10, from my calculator, I'm getting 1 out of 5. And if I'm getting 1 over 5 as 1 over RT, then resistance total shall be the reciprocal also on the other side, which is just 5. So we would have gotten the same answer at this point where we got 5 using the general about parallel resistors. So when resistors are in parallel, or when components are in parallel, their resistance varies in this formula. But when in series, total resistance equals to sum of the individual resistances. A very interesting question in number 8. A positively charged rod is brought near or close to the cap, a leaf electroscope. The cap is earthed momentarily by touching with the finger. Finally, the rod is withdrawn. The electroscope is found to be negatively charged. Explain how this charge is acquired. In simpler terms, we are explaining how to charge an electroscope using the induction method, not the contact method, the induction method. And I will start by doing it on a diagram of the cap here. Then we have the leaf at that point. You have the leaf there. So let's look at this. This is the golden leaf. This one is the metal plate. Then this is the cap. Now, what are we doing? We are bringing close a rod. This rod is positively charged. We are not touching the cap. And therefore, it means this. When the rod was brought close the negatives were attracted. And as long as it is held in place here, the negatives are going to be attracted. The negatives are going to be attracted. And what happens? We will have the positives repelled to the leaf and to the metal plate. So positives get repelled to the leaf and also to the plate. But the negative charges are being attracted and held. As long as the positive rod is in position, the negatives will remain held there. They are already held there. So now we would say this, because they are held there and negatives have been repelled to the leaf, then now earthing is done at this point. You earth now with your finger like that. Electrons shall move from the earth up. It is electrons which move, remember. During earthing, it is electrons that move either from the ground to the conductor or from the conductor to the ground. So it depends on the charges which are free at the time you are earthing. So when we are earthing, we are having free positives there. And therefore, the positives will attract electrons from the ground, because we can't say that the positives will move to the ground. No. The negatives at the cap are held by the positive rod. So those ones will not move. They are held in position by the positive rod. Therefore, electrons now will move from the ground to neutralize the positive charges at the leaf and the plate. At the leaf and the plate. And at that moment, we say, now, at the end of it now, we shall remain with the rod holding negatives in position. And when you withdraw the rod, because the negatives are like charges, and we know that like charges repel one another. In the process of repelling one another, they shall spread now to the plate and the leaf. And this particular electroscope now shall be negatively charged. So from that diagram, I am very sure, from that particular diagram, I'm very sure that now you can make a conclusion that negative charges be realized at the end of the day. So now we can write the simple procedure or the simple explanation in this manner. The rod attracts the negative charges and repels the positive charges. When earthed, the positive charges are neutralized by electrons from the earth. Electrons from the ground. When the rod is withdrawn, the electrons or the negative charges as they repel one another now, spread to the plate and the leaf, the golden leaf. So the electroscope shall become negatively charged. And that is why there will be some divergence at the leaf of the electroscope. That is why there shall be some divergence at the leaf, the electroscope. Look at number 9. A soldier standing some distance from a wall blows a whistle and hears its echo 1.2 seconds later. How far is the wall from the soldier? In brackets, we are given the speed of sound in air as 330 meters per second. 330 meters per second. So we shall say that generally speed is given by distance out of time. But in this particular case, echo, the distance is usually covered twice, because after blowing the whistle, we expect the sound to move to the wall and back to the ears of the soldier. Therefore, speed is given by twice the distance out of the time taken. Twice the distance over time taken. 330 equals to twice the distance. Twice the distance out of the time taken. So we can say that time is known. Sorry, time is known as 1.2. Yeah, as 1.2. Therefore, we can now get the value of this particular distance from our calculators very quickly as 198. 198. Then number 10, as we wind up with section A. The table below carries information on the type of radiation detector and use for some electromagnetic radiations. Okay, it's only one. So we have a dash on the type, but the detector is a thermopile blackened bulb thermometer. Then the use is a warmth sensation. According to this use and the detector, we're supposed to talk about infrared. So the radiation here is infrared. Remember to come up with a chart, even yourself, as a student. Even as a student, plan to, plan to get a chart of all the types of radiation, all their detectors, then their possible uses. Because on this topic, which is very simple, which is very simple, it is usually summarized into those three: the type of a radiation, the detector that detects the particular radiation, and also the use of the radiation. So that is all about section 1, section A, that is. We go to section 2, whereby we are now going to cover 55 marks, compulsory marks. Compulsory marks. State 2 conditions which must be satisfied for total internal reflection to occur. And one of these conditions, we usually say that the ray of light must be traveling, or must travel from, the rays of light must travel from a denser or optically, it's good to use optical density, an optically denser medium to an optically less dense, to an optically less dense medium. Then something else that is about, I'll be explaining actually point 1. I'll be explaining the angle of incidence in the optically denser medium, must exceed the critical angle. Must exceed the critical angle. That means you should be understanding what critical angle is. Let's get back to the space up here. We are talking of two media here. Media 1, media 2. So when a ray of light, this is the normal. When a ray of light travels from an optically denser medium to optically less dense medium, the ray of light usually is reflected away from the normal. Away from the normal. That is the case we are talking about. If a ray of light is moving from an optically denser medium to an optically less dense medium, the ray of light is reflected away from the normal. Away from the normal. Now, if it is away from the normal, and on the other side, it is the opposite. If we are moving to an optically denser medium from optically less dense medium, once a ray of light strikes the interface, it gets refracted towards the normal. So in this case, it's towards the normal. In this other case, it's away from the normal. Away from the normal. So it is in this case whereby, as we continue to increase the angle of incidence, at some point, this ray shall go through the interface whereby it will be making the angle of refraction 90. And with the time, because this, as we increase the angle of incidence, the angle of refraction also increases. So it shall increase until the ray, instead of coming to the second medium, now it gets totally internally reflected, such that it doesn't penetrate to the second medium. So that's why we say, for this particular case, whereby the ray of light is moving from an optically denser medium to an optically less dense medium, it is the case where at some point, total internal reflection is likely to occur. Now, considering the second setup, there is no way total internal reflection shall occur because the refracted ray is towards the normal. So there is no way it will bounce into the first medium. No way it shall bounce to the first medium. Then about the critical angle, if this continues in the first case, if it continues until the ray now is through the boundary that way or through the interface that way, such that the angle of incidence, the angle of refraction has become 90. At that point, the angle of incidence shall be called critical angle. So the angle of incidence in the optically denser medium, for which the angle of refraction is 90 in the less dense medium, is called the critical angle. Now, if you increase angle of incidence beyond critical, it means now instead of refraction, we shall have total internal reflection. So that's why we are saying total internal reflection must occur if and only if the angle of incidence has exceeded critical angle. I hope we are together there. Please remember to subscribe. Remember to subscribe for content. If you want physics content, if you want to get the best, kindly just be a subscribed member of Shifting Grades. The diagram below shows two rays of light incident normally on face PQ of a glass prism. Whose critical angle is 42. Remember, This is 90 degrees, according to the sample there. This is 45. So automatically, this is a 45. That's something I want you to understand first. That one is a 45. Then now, beyond there now, we're supposed to get to the question. I hope you've taken into account that the critical angle is 42 degrees. If the critical angle is 42 degrees, ladies and gentlemen, we can proceed to respond to a few things here. And what are we responding to? Complete the diagram to show the path of the two rays as they pass through the prism. So as they pass through the prism, how are they going to behave? When there is no angle of incidence, there is usually no angle of refraction. In that case, we say, if the ray is through the normal, or rather, if the angle of incidence is, okay, if the ray is perpendicular, there is no refraction. So the ray passes undeviated. This one passes undeviated all the way to the other medium. Same to the other one. The rays pass undeviated. The rays are supposed to pass undeviated, that too. So it's good to indicate arrows. The rays just proceed undeviated. Now, if they are proceeding undeviated, it means we can do normals at the point where they are incident to the second side. So we draw a normal at this point. We draw a normal at this point. You see? So we draw normals like that. If you draw a normal, which is of course now perpendicular to this particular face, we are supposed to ask ourselves, this is 90 because the ray passed undeviated. We have a 45 at the corner here. Therefore, the angle here is also 45, and the one here shall automatically be 45. And this now becomes the angle of incidence. For this particular phase now, for phase PR, for PR, it becomes our incidence. The angle of incidence is 45. Do you know 45 is greater than 42? The 42 up there, the critical angle. So if the angle of incidence is greater than critical angle, there will be total internal reflection. So the ray will not go outside to the air. It shall be totally internally reflected. So and the angle of reflection is supposed to be equal to the angle of incidence, which is again 45. So it shall be now 45. It shall be 45. And also the other one, it shall be through 45. Therefore, this is what we are talking about. This is also 45 according to the laws of reflection. The ray proceeds like that through 45. And also 45 here. So the ray shall proceed like that. When the ray is proceeding like that, it's good for you to know that if this is a 45, and also this is 45, this is 45, that is 45, it means the ray at this point, we are having 90 and also 90 here. And just as the rays entered, they shall exit undeviated. The rays are going to exit undeviated back to air again. So that's how the rays are going to travel through the space. This is called geometrical optics, the behavior of light as light traverses from one media to another. Part C of this particular good paper. A pin is fixed horizontally at the center, mark the word center, of a rectangular container with thin transparent wall as shown in the diagram. So we have the pin, rectangular container, 16 centimeters depth. Now look at the question that follows. A transparent liquid is then poured into the container when viewed from side A. Let's look at A. When viewed from A, A is here. When viewed from A, the distance of the pin is 6 centimeters from the surface of the liquid. Determine the refractive index of the liquid. So we pour liquid into this rectangular container. Then instead of seeing the pin being at the center, which should be now 8 centimeters at least. Instead of viewing it at 8, we start viewing it somewhere here. We start viewing it at 6 centimeters. We're supposed to interpret the question very keenly and in that manner. There are people who will use 16 centimeters, yet the pin is placed at the center. So at the center means the geometrical center of this height should be 8. Determine the refractive index. We know there are very many formula to determine the refractive index of materials. So refractive index is given by real depth out of apparent depth. The real depth of this pin is 8, but apparently it appears to be 6. Therefore, refractive index without units is going to be 1.333. No units for refractive index, just a value. You are supposed to be able to neutralize. You should be in a position to really understand a question in such a manner. The figure below shows a coin placed in a larger empty beaker. Look at that. We have the observer somewhere. We have the coin. We have the container. An observer looking into the beaker from the position is unable to see the coin. Sketch 2 rays from the point on the coin to show how the observer is able to see the image of the coin after the container is filled with water. So when we fill this container with water, there will be some reflection, and this guy is able to see. This guy is able to see. Therefore, this is what shall happen. This is what shall happen. From the coin, we can have rays. Okay, because light does not negotiate corners, then you can say the guy will be able to see the coin at some point here. The guy will be able to see the coin at some point. So what will be happening here is that from the coin, the real one, from the real one, shall have rays of light moving up like that. Rays of light moving up that way. Then now they shall be bent now. The rays now shall be bent. Yeah. The rays are bending. As they emerge from as the rays emerge, they will be bent. And now the observer will be able to see this particular coin now. Image of the coin. The image of the coin now will be seen somewhere there. That is where the image of the coin shall be seen. All right, because it is lying on the other side, it will be seen this way. Let me show you. This other side shall be. The coin will be seen somewhere here. That's where the coin will be seen. That is how it shall be observed. Number 12, on waves. The figure below shows the displacement time graph. Wave traveling at 400 centimeters. Determine for the wave the period. Period is the distance. No, period is the time taken to cover a complete oscillation. Time taken to cover a complete oscillation. What is an oscillation? The distance between 2 points which are in phase. 2 points in phase. So we're going to consider the number of waves here. So from that point, we shall say that all the way from that point, or we can consider here, let's consider point A, please. Point A, until at point B, we are having a complete oscillation. We are having a complete oscillation. If that is a complete oscillation, then we would say this. that we have from A to B, one oscillation or one wavelength. We might call it that. So that complete oscillation now will be added to the other part of this wave, because according to this calibration of time, we are only having 0.8 time difference at that particular point. Therefore, the other one now shall be, we have a half. This is our from B to C. That's a half a wavelength. And also, we can say that the portion from C to D, when added from A to O, we shall have another half. So this is a quarter wavelength, and this is a wavelength. And therefore, we can say we have two wavelengths here. The time taken to cover the two wavelengths is 0.8. Now, if that is 0.8, ladies and gentlemen, then we can ask ourselves, what about one oscillation? It shall be 1 times 0.8 over 2. So we are getting 0.4 seconds as the periodic time. Okay, let me check a simpler way of coming up with this particular thing. I think we are struggling so much anyway. Let me think louder. This is 0.8. So when we consider all these intervals, we have 1, 2, 3, 4. Then the fifth one is becoming 0.8. So if we say this is 0.2, and this is 0.4, then this is 0.6. This really the right labeling, okay. 0.6, 0.2, 0.4, 0.6, then 0.8. No, I think it's not the right thing. Let's just consider what I have done. That one will not be well interpreted. Let's just talk about the two complete waves are being covered in 0.8 seconds. What about one wave? One wavelength shall be in 0.4. 0.4. Then part two, the frequency. We need the frequency. Frequency is usually given by the reciprocal of T. So the reciprocal of 0.4, 1 out of 0.4 shall give us 1 out of 0.4 shall give us the value, and this is 2.5. Remember, every quantity should be given in its own SI units. And for frequency, we talk about Hertz. For frequency, we talk about Hertz. Then the other thing is wavelength. We know that generally, speed in a wave is given by F lambda. Therefore, lambda, which is our wavelength, will be given by C out of F. Let's find C first. C is the velocity. According to the instructions here, we are told that this particular wave is traveling at a speed of 400 centimeters per second, which means the units can be converted to SI units. 400 centimeters can be converted to 4 meters per second. So the speed is 4 meters per second. So we'll talk about 4 meters per second. Therefore, wavelength equals to 4 out of 2.5. 4 out of 2.5 shall give us 1.6 meters. Because it is wavelength again, it should be in meters. Your wavelength is usually given in meters. The figure below shows the setup used to demonstrate interference of sounds or sound waves. We have two speakers. Then the two speakers, we can see the two speakers. We can just see the distance. We can see a path here, X, Y. Then now we can go to the first question. Why are the loudspeakers connected to the same audio frequency generator? This is to ensure that they give coherent sources to make sure that they are coherent sources of waves to ensure that they are coherent. That one is the main word there. Sources of sound. To produce sound which is having the same frequency. The same frequency. That's why this one is not having its own source. This one is not having its own source. They must be connected to the same audio frequency generator so that now the sounds produced from the two speakers are coherent, having the same frequency and also having a constant phase difference. A constant phase difference. So that interference may happen very well throughout the path CO. An observer walks along XY. Look at XY. State and explain the observation made. This guy, the observer, he observes or she observes what we call a loud sound, and also she is going to, or he is going to experience soft sound. So he observes loud sound alternating. Loud sound alternating with soft sound. Alternating with soft sound. Then what else are we supposed to mention at this? Just an explanation. The loud sound is due to constructive interference. Constructive interference. While the soft sound is due to destructive interference. Destructive interference. Destructive interference. What will a student hear if he moves along OC? So we have OC. Along OC, they are going to experience a constant loud sound. Constantly, they shall experience loud sound. State the effect on the observer along XY when the frequency is reduced. So when you reduce the frequency, okay, can we begin by increasing so that now we may state the opposite? When you increase frequency in the audio generator, the sound will be having a higher frequency. And now we will say that the time interval between the loud and the soft sounds shall be decreased. Shall be decreased. The time interval, because we are saying the speaker experiences loud and soft sounds alternating. When you increase frequency, now the intervals he was taking to hear the different sounds, those intervals shall be reduced. Now that we are reducing the frequency of the generator, we will have the distance or the time interval increased. So the time interval between the loud and the soft sound is increased. The time interval between the loud and the soft sound is increased. Which is increased. Number 13, this is on electrostatics 2. Yeah, electrostatics 2. The diagram below shows a parallel plate capacitor with a dielectric material in between the plates. So we can see plates and a dielectric material in between. State how each of the following quantities are affected when the dielectric material above is replaced with another of higher permittivity. We should know that capacitance is directly proportional to area of overlap, but inversely proportional to the distance of separation. So we say that now this equation or this relation can now be substituted with an equal sign. Then we introduce a constant, which is called now the permittivity of the material, or permittivity of the dielectric material. So with that case, then we will say that capacitance and the permittivity of the dielectric material are directly proportional. So directly proportional when replaced with another of higher permittivity. So for higher permittivity, we would say capacitance is increased. That's why I've started there. Capacitance is increased. If capacitance is increased, then we know that charge equals to CB. Capacitance times voltage. And now we need voltage. Capacitance has increased. So we know that voltage equals to Q out of C, meaning that voltage is inversely proportional to capacitance. If voltage is inversely proportional to capacitance, then we can say that because capacitance increased, voltage has to decrease. Voltage decreases. There are some questions, depending on how you approach them. Anyway, I'm not encouraging anyone to use my technique. Maybe there is another way you can do, and you begin by responding to part 1, then part 2. But according to me, I like relating things mathematically. So I would encourage people to embrace the same. If there is a certain mathematical formula that you can relate to know the relationship between two particular quantities, so that from that relation, you are in a capacity to mention or to derive the effect on one when another one is increased or decreased, please use the formula. Just use the mathematical formula to come up with simple statements like increasing and decreasing. Anyway, part B of the same. The figure below shows a circuit in which capacitors are connected to a 12-volt source. Study the circuit and use it to answer the questions that follow. As we study the circuit diagram, please be invited, if you are joining us late, that we have a very serious program here. This is the center of all the knowledge. Kindly come over, come on board, come on large numbers. Please turn up with your friends, enroll for this simple program whereby you shall learn the best from, of course, the best tutors. If this is how I'm teaching, then you can just imagine the kind of people that I'm bringing on board. Please be assured of some quality presentations from the tutors that we're bringing on board on physics, chemistry, biology, mathematics, Kiswahili, and English. We are bringing you the best, and you shall get the best from them. 0704 15 33 66 is the number you're supposed to consult through. So please reach out for the program. So we are having a 4, 2 microfarads, 3 microfarads. And the first question is effective capacitance. Now, unlike resistors, for capacitors, when they are in parallel, we add them direct. So the 4 and 2 shall be replaced by 4 and 2 are equal to a 6 microfarad capacitor. Now, the 6 microfarad, now we shall be having, let me sketch it now. We shall be having 6 microfarad in series with 3 microfarad. If that is the case, then now we can say, now that they are in series with one another, for capacitors total now shall be the product of the two out of the sum of the two, 18/9, which is 2, microfarads. 2 microfarads. This can also be written as 2 times 10 to the power of negative 6 farads to ensure that you are working with SI units. Yeah. So 2 microfarads. No, 2 times 10 to the power of negative 6 farads. Instead of microfarads, now we make them SI units. Optionally anyway. We are also told to find the charge on the 2.00 microfarad capacitor. Something that we're supposed to notice is that charge is given by CV, as I had quoted up there. And charge behaves like current, because anyway, the rate of flow of charge is what we call electric current. The rate of charge flow is electric current. Therefore, we are supposed to know that the total, we are having this one, and we are having effective capacitance. So we can get the charge in this system. Charge in the system. So total charge in the system shall be C, which is 2 times 10 to the power of negative 6. This one multiplied by 12 voltage supply. And this shall give us, let me multiply that. 2 times 12. It gives us 24. So it's 2.4 times 10 power negative 5 coulombs. That is the total charge. So the total charge flows through the 3 microfarad. That is the total charge flowing there. And now you should know, if the total charge flows there, there is the voltage drop at that one. So we can get the voltage at 3. Voltage is given by Q divided by C. Q divided by C. So we shall have Q divided by C. The C there is 3.0 times 10 power negative 6. So what is the voltage at? What is the voltage at the 3 microfarad capacitor? This is going to be 8. So we're going to have 8 volts. So we have 8 volts here. Voltage here is 8 volts. Now, we are supposed to know that from 12, we have a voltage of 4 now remaining. And the voltage of 4 shall be distributed equally here. We shall have, because of the parallel nature of the setup, when voltage is in parallel, it is usually the same. Components in parallel have the same potential difference. So 4 shall be uniform at the 4 microfarad and also at the 2 microfarad. But the 3 microfarad is having 8. Therefore, for the 2 microfarad now, we can talk about the charge there. Charge at the 2 microfarad will be given by the charge there, the capacitance there, which is 2.0 times 10 power negative 6, I'm making it as a unit, times the voltage there, which is the voltage there. Now we have confirmed that it is 4. Just confirmed that the voltage there is 4. So now this can be computed as 8.0 times 10 power negative 6 coulombs, because it is charge coulombs. Or 8 microcoulombs. 8 microcoulombs. If we use unconverted charge, we shall get microcoulombs. Yeah. We also told to find the potential difference across the 3. Actually, that one I've already calculated. Potential difference across the 3, it was the first thing that I did. Voltage across the 3. So the working for that question is already done here. Voltage across the 3. Yeah. So now This one is done. Please revisit. Just scroll back and check what we have said about the voltage at the 3. We have done it already. Energy stored at the 2. We know that energy is equal to, okay, it has several formula, but half CV squared is 1. So when you talk about half, C is capacitance, 2.0 times 10 power negative 6. I'm trying to make it as a unit, times the voltage there, which is 4, now squared, which is 4 squared. So this is exactly going to give us 1.6 times 10 to the power of negative 5. Because it is energy, we talk about joules. Yeah, now that it is energy, we talk about joules. Number 14, ladies and gentlemen. Determine the term electromotive force, EMF of a cell. This is the total voltage, or the voltage across the ends, across the terminals of a cell in an open circuit. In an open circuit, or when the cell is not supplying any current. It can be a cell or a battery. When it is supplying no current. The graph below was drawn from results obtained during an experiment to determine the EMF and internal resistance of a cell. Use the graph to answer the questions that follow. So we have the graph here to answer the questions that follow. The first question is determine the EMF. The second one, internal resistance. Okay, let me begin by saying this, that EMF is given by terminal voltage plus lost voltage. So voltage equals to E minus the lost voltage. You know, lost voltage is current times internal resistance, because lost voltage is lost due to internal resistance, and V equals to IR. So it is the current flowing times the internal resistance. So we can rearrange this and say V equals to negative IR plus E. Now, if this one is plotted on the y-axis, then current is plotted on the x. Then we will say the constant here becomes our C. So EMF is read from the y-intercept of the particular graph. Y-intercept. The first mark will go to a student who is able to extrapolate the line and see the y-intercept. A student who is in a position to extrapolate the graph and tell us that the EMF is exactly 1.5, and this is a 2.0. So I'm seeing 0.5 volts being represented by 10 units. What about the units represented by the 2 units that I'm seeing beyond 1.5? It shall be 1/10, which is 0.1. So this is 1.51. 1.51. So the EMF, which is the y-intercept, equals to 1.51 volts. I've said in the interpretation of the scale, I want us to look at it carefully. We can say this. 0.5 volts from 1.5 to 20 are represented by 10 units. What about 1 unit? What shall it represent? 0.5 times 1/10. So we can see one small unit is representing 0.05. 0.05. If it is 0.05, then we need to multiply now 0.05 by 2. So for this case, by 2, it shall become 0.10. And therefore, this is 1.6. Sorry. That is at 1.6 volts. 1.6 volts. That is now the EMF of this particular cell. 1.6 volts. The total internal resistance, internal resistance of the cell. We've said V equals to negative IR plus E. So that this was Y-intercept. So now the coefficient of, because current is on the x-axis, according to the graph, current is on the x-axis. Therefore, negative R becomes the gradient. So the coefficient of whatever is in the x-axis becomes the gradient. Therefore, negative R equals to the slope. So from the graph, we need the slope. We just need the slope. We just need the slope. Therefore, according to the slope, we have coordinates 0, 1.6. Some of the coordinates are 0, 1.6, according to what we've just prolonged, 0, 1.6. Then other coordinates now can be at this point. Let me just read the value. At this point, we can talk about 0.35 and 0.25. 0.35 and 0.25. Those are some of the coordinates on the graph. So we can get slope. Change in Y, 0.25 minus 1.6 out of 0.35, change in X. So 0.25 minus 1.6, this gives us negative 1.35 out of 0.35. So when we divide by 0.35, we are getting negative 3.8. Negative 3.857. So we are saying negative R equals to negative 3.857. So what will be R? We divide through by the negative. Because it is resistance, then it shall be in ohms. Just like any other resistance, it is in ohms. So that's how we work it out. At number, okay, we are winding up, ladies and gentlemen. Don't worry. Don't worry, we are almost doing it. Draw an appropriate circuit that was used to obtain values to plot the graph. So for this particular graph, we will need a circuit diagram, which is very simple. Some cells or cell, actually it's likely to be one cell, sure, because of the nature of the potential difference you're getting. Then now on this, we can have an ammeter connected here. We can have a switch, somewhere. Yeah, we can have a switch. Have a switch there. Then we should have a variable resistor here. Variable resistor. So at this point, we can talk about a variable resistor. When you use it this way, we mean it's variable resistor. And actually the jockey at this point, will serve as the switch. Then there is something called voltmeter. A voltmeter should be connected across the components and not in series. And we all know the reasons. The reason why the voltmeter, you can use the comment section actually to tell us, why do you think that the voltmeter is connected across and not in series with the other components? Why do you think so? An electric heater rated 3 kilowatts is switched on 12 hours daily for 2 weeks. Given that the cost of electricity is 20 Kenya shillings per unit, determine the electricity bill for the 2 weeks. Let's get the units first. Total units. Units of power. Power consumption, which are supposed to be in kilowatt hours. We have 3, that's the rating, times 12 hours. Then we multiply this one by the days of the 2 weeks. And we are going to get 504 kilowatt hour. So when we say per unit, we mean per kilowatt hour. This is now domestic wiring. So the bill now, the total bill for this particular week shall be 504 for the 2 weeks times 20 per unit. We're getting 10,080 Kenya shillings. 10,080 Kenya shillings at number 15. The first thing that we're supposed to do here is to state the Lenz's law of electromagnetic induction. Remember also to state the Faraday's law during your own time. Those are the common laws which are in electromagnetic induction, form 4. The direction of the induced EMF, this is the statement of the law. The direction of the induced EMF is such that the induced current which it causes, the induced current which it causes produces a magnetic effect. Magnetic effect that opposes the change produces it. That opposes the change producing it. The change producing it. That opposes the change producing it. The transformer above should be below. The transformer below used to power a substation as an input of 30 kilowatts. That is the input power at a potential difference of 5 kilovolts. The secondary coil of the transformer has 1,000 turns and it's used to step down the voltage to 1 kilovolt for consumption. You can see the input power and voltage. The output voltage can also be seen. The number of turns can also be seen. Assuming the transformer above is 100, is 80% efficient, calculate the current in the primary coil. So in the primary coil, we have the power and we have the voltage. And we know that power equals to VI. Therefore, the power, which is 30 watts, 30,000 watts, 30 kilowatts means 30,000. Then 5 kilovolts means 5,000. Then times now the current. So the current shall be, we take 30,000 and we divide. We're going to get 6 amperes. 6 amperes, that will. Look at the second question on that point. Look at the second question on that point. The number of turns in the primary. There is something called the turns ratio. The turns ratio. Turns ratio says that V out of V in the primary equals to the number of turns in the secondary over the number of turns in the primary. So voltage in secondary over voltage in primary equals to turns in secondary over turns in primary. That is called the turns ratio. Now, for this particular case, do we have a voltage in secondary? Yes, it's 1,000. 1 kilovolt. Then in the primary, we are having 5,000. This one should be equal to turns in the secondary, unknown. Turns in the secondary is known to be 1,000, sorry. Turns in the secondary, turns in the primary ndio unknown. Yeah, turns in the secondary, 1,000. But in the primary, it's what we are calculating. So we need 1,000. 1,000 N equals to 5,000 by 1,000. So number of turns in the primary equals to 5,000. Wow, 5,000 turns that way. Simple mathematics, you cross multiply at this point. So that's 1,000 NP equals to 5,000 by 1,000. So that 1,000 divides to remain with 1,000. Current in the secondary. Current in the secondary. Current in the secondary. So at the secondary, we can find what we call, first of all, what we call power output. So power output equals to 80% of the power input, because this one is 80% efficient. So power output shall not be 30,000. It shall be 80% of that. There is power wastage of 20%. So 80% of this shall be 80% of 30,000 shall be 24,000 watts. Meaning now this power of 24,000 is given by, power is given by voltage multiplied by current in the primary. So current in the primary shall be exactly 24 amperes. Yeah, 24 amperes. 24 amperes. I'm trying to see whether there is an alternative that we can use. Because in the primary, in the secondary, we are having number of turns. We're having number of turns in the primary. Let me check. Let me just check on alternative. Let me check. Number of turns in the secondary over number of turns in the primary should be equal to current in primary, current in secondary. We interchange for current, not like voltage now. We interchange. So with this, we can say in secondary, we are having 1,000. In primary, 5,000. This is equal to current in primary, which we calculated as 6 out of current in secondary. Current in primary is 6. What about current in secondary? Remember, this current was in secondary. Sorry for that. Yeah, secondary circuits. So when I take 1,000, okay, 6 times 500, then I divide by 1,000. I'm getting 30. No. So we can omit that working unless there's something we are not substituting right. Unless there's something we are not substituting right. But we should know that should know this. Actually, I'm just going to give you the relation according to turns ratio and current, so that it might help you to work out some things. So we're talking of voltage in secondary over voltage in primary equals to number of turns in secondary over number of turns in primary, which is equal to current is interchanged now. Current in primary over current in secondary. I want to see whether we can now apply this one. Voltage in secondary. Voltage in secondary. Voltage in secondary is 1,000. The other one, 5,000. 1,000, 5,000 equals to. Oh, sorry. This is for an ideal transformer. Sorry. For ideal transformer. Ideal transformer. So for an ideal transformer means that a transformer with 100% efficiency. Sorry for that. 100% efficiency. So now we cannot apply here unless we get back to the issue of efficiency. So for an ideal transformer, which is not losing any power, that is what we could have applied. Sorry for that. Yeah. This one now, this one is losing some power. It is having an efficiency of 80%. A magnet is moved towards the end of a stationary coil and current flows as shown. So current is flowing in this direction. State the polarity of end A. State the polarity of end A. Look at this. According to the diagram, we can use what we call, we have a clock rule whereby we can check the direction of flow at point P. If we say this is P, at point P, when you observe the direction of current, it is in the clockwise direction. And if it is in the clockwise direction, that is a south. According to the clock rule, P is a south pole. And automatically Q a north. If that is a south pole, then we are supposed to get another south here and a north here. So A is a north pole. The reason why we are saying this is a south is because according to the law of Lenz's, the EMF induced here should oppose the magnetism which is producing it. It should induce a magnet that opposes the one producing it. So it should produce an equal, or it is having an equal, the same polarity at that point. So a south is there, meaning that on the other side, we have a north. State two ways in which the magnitude of the induced EMF can be increased in such an experiment. In what you call electromagnetic induction, EMF can be increased using a number of ways. One is increasing or using a stronger magnet. Stronger magnet is one of the ways. Then after stronger magnet, we can talk about number of turns on the coil. Increased number of turns. On the coil, we can also have the speed of the magnet. Increasing the speed of the magnet. Remember, in this case, it is magnetism producing current. In form 2, magnetic effect of an electric current, it was current that produced magnetism. In form 4, under electromagnetic induction, magnetism produces current. Thank you so much for following. Remember to subscribe and share. Remember to enroll to our program here. Reach out through the number attached, 0704 15 3366, and get connected to our programs. Otherwise, thank you so much. Remember to subscribe.